So with that said, I'd like to introduce our main presenter, Albert Rooks. He is the CEO of WaterDrop Systems and a recognized leader in the sustainable heat pump water heater industry. Answering questions behind the scenes is Ben Wong, our WaterDrop sales manager. And so with that, I'll turn this presentation over to Albert from WaterDrop Systems.
Great. Thank you very much, Taylor. Okay, well, we'll get started. Again, my name is Albert Rooks and founder and CEO of WaterDrop Systems. And we have been developing this company for, I want to say, about 4 years right now, after doing a series uh, of research projects around central heat pump water heating and just many site build-up systems, all in development to get us to the point where we have some really interesting systems and a scaled solution that is being really well accepted in the market. So the company goals for us is we really want to be a full solution company, full solution partner. So we really want to start with sizing and conception of the project, work all the way through with design, specification, and then as the project goes out, our distributors are able to then work with also sizing and design, but all the way through tender and delivery, and then startup and operation of the system. We've added some new features recently. You'll see some at the end of the slide that talk about maybe ongoing operation and ongoing relationships of the domestic hot water systems. So really full solution, and it's a really interesting time in this industry. We've got a lot of new tools and new refrigerants to work with, and for us, really everything we work with is a transcritical CO2 refrigerant. Um, the fellow on your screen on the left-hand side is a researcher here based in the Pacific Northwest, same town that we're in, and we got to learn from him and his research starting about a little over a decade ago, and then start developing kind of understanding of how CO2 works and why we like it. CO2 is really a good refrigerant for water heating, not so much for space heating or space cooling. It's something that, as we understand it more, it works and it crosses a transcritical boundary and it creates a whole lot of heat. And then we've got the task of managing that heat. So it's really good for big lifts, and domestic hot water is really a big lift. You want to start with an entering water temperature, and you want to work up to as high a storage temperature as you reasonably can. So the thing about CO2 that Ken's research found was really that the refrigerant works in all climates. We can be in very warm climates, and we can be in very cold climates. We can get the refrigerant to operate within very predictable, reasonable bounds. And therefore, line two shows that really for this refrigerant in our application, there is no defrost rate. Or derate, sorry. Defrost is accomplished by a hot gas bypass rather than a reversing, because as we'll talk, we're going to be working with the refrigerant in really high pressures, about 1400 to 1800 psi, and because of that nature, and the fact that we don't need a defrost derate, we can size it to loads and get a really stable and reliable leaving water temperature all the way down to minus 14F. We can go lower, and I've seen it go lower, but really minus 14F is an area that it's very comfortable in working in. And so really all that leads up to with CO2 in this application, there's no capacity loss all the way through 5F. The individual heat pumps that we're working with have a heating capacity of 4.5 kilowatts. We've got predictable flows coming out of the leaving water temperature, and we really understand the operation. Not having to do these derates and capacity losses across all these ambients allows us to kind of treat plants a little bit differently. So here's kind of how it works and why we like CO2. The transcritical nature allows for really efficient heat exchange. And and that's really kind of pictured by these attributes, if you will. So CO2 in this application operates more like a gas cooler instead of maybe a water side heat exchanger. They kind of look the same because it is a pipe of refrigerant next to a pipe of water, but the relationship is a little bit different. So if we follow the red line at the bottom to the right, and we're just cruising along, and then we hit the compressor. The compressor charges it up, and at the top there where we say 105 C, it'll be at a working pressure of roughly 1400 psi, 1400 to 1800 psi, and at that point it's crossed the transcritical boundary, uh, and essentially we can call it transcritical, supercritical. Essentially, what this all means is that when we've got the refrigerant under that much compression in this application, then it takes on the density of a liquid, so it's very dense. There's a lot of heat in it, but it's still in a vapor form, right? So there's not really a full phase change here. So what we've got is this high pressure, high temperature vapor, and we can run that vapor through a gas cooler. So really all we're doing is sending that vapor down to drop its energy. And the blue line is receiving that energy, and that's really the pipe of water. So we just run a pipe of potable water, kind of, in a heat exchange application, but more like a gas cooler because we've got a gas and we're taking the heat off of the gas, and because of that super high temperature, super high density, but still a vapor, the crossover from one to another is really fast, and there's really not a lot of loss. And the interesting thing about CO2 and the units that we use is the actual operation of pumping it up to that high pressure, high density application in compressor energy is not really a lot. And because we're crossing a transcritical boundary, we don't need a lot of ambient energy. The ambient energy from the air on the evaporator is just a big bonus. We could actually accomplish the whole transaction without a big bump of ambient energy. So we'll see actually some COPs here in a little minute. But that brings us to being able to work with water heating a little bit differently. So it allows us, because we don't have these D rates and we can work in all these ambients, and we can maintain capacities down to very cold temperatures, we can size the applications right to the full heating capacity. So we can really kind of right size the equipment, and we don't need to adjust equipment sizing for D rates. So we don't apply a defrost D rate. We have heating capacities exceptionally high, 5 degree Fahrenheit at 2.25 COP, and 45 we've got a 4, and 80 we've got a 5, and that's just heating. It's not a combined COP, just heating COP, and that's really unusual. And those ambients are our working ambients across North America. We bump into some issues using potable water in very cold climates. It's not really anything to do with the refrigerant. It's more really about how the system operates and gathers the energy and gives it off to the plant. So it just means that we can come in and size a plant capacity right to the load. So we've got a long history on this, and we're in a transitional industry. So some of the projects started about a decade ago in looking at how to do these central heat pump water heaters. And it's really been an interesting development. Originally, it's kind of the classic design of you have heat pumps, you have storage tanks, you have now a swing tank, which we'll talk about here in a few slides. And then the usual suspects of expansion tanks, controls, mixing valves, recirc pumps, service panel to control electrical flow and so forth. And it's been typical to make site built up systems like the one we're looking at. And this was done a building downtown Seattle, wood frame, 5 or 6 story, multifamily residential. And so for this building, it's quite common in some of these colder climates is to house the domestic hot water plant in a wooden box on top of the building. And in this case, the heat pumps are up on the roof of that box on your left-hand side of the screen, and the tanks are inside. We've got big sliders so we can get the tanks in and out. And then we lay out the piping and the rest of the components of the system on the wall. Pretty big, pretty big endeavor there, right? We've got to build a building, we've got to design kind of a doghouse or a plant house on top of the building. It's got to be design spec, it's got to meet building inspection requirements, seismic requirements, and then we go up, we put the heat pumps on the roof. We got a number of penetrations. For every heat pump up there, we've got a disconnect. So a lot of parts to manage, right? So what we really think about as we participate with some of the utility partners and development partners that we're working with is that the goal is to be able to scale heat pump water heating in these larger central plants over the next period as we kind of decarbonize these buildings. So, so because it's a bit of a tricky craft design, kind of like a craft-based design, custom design for every building and every application, that's a lot to accomplish at scale. So the Advanced Water Heating Initiative has been looking at this problem or this challenge for quite a long time. And basically what they've come out with is the best way that we can accomplish this and de-risk for everyone in the industry and allow kind of an aggressive scaling is to package. And, as an industry, we've packaged before, we understand how this works. And so our company really developed North America's first fully packaged domestic hot water system for multifamily buildings using heat pumps and storage tanks and all the controls and so forth. So this is what a package looks like. So it's all the panels are off, and really the panels are removable and all these things. And so we can see kind of heat pumps on the left-hand side. They're hanging off the unit. They're all piped inside to central manifolds. A big white primary storage tank in the back, a 9 kilowatt swing tank in the front. These vary now, and of course, you need different size equipment so we can vary how many tanks are inside, how big the frame is, how many heat pumps are outside. In all plants, we need a controller, and the controls are something that we've spent a lot of time and development on, and they're getting more and more interesting with more capacity every day. Because we're going to store at high temperature around 150 degrees, we'll need a mixing valve, we need expansion tanks, and really, this is a water heater. So this could be lifted on top of a building, set, attached to the building, and then the lower left-hand corner shows 3 building connections. So cold water supply, hot water out, mixed hot water out to the loop, and then recirc return. And then a single power landing. The power landing actually goes right about where that label that says electronic mixing valve is. Panel goes on, and then the insulated panel goes on, and then the power panel goes on top. And then it's a single 208, three-phase 208 connection on the building. And that's a water heater. It's got water, it's got power, it's got all the controls, it's ready for startup. And these can be maybe set and started up in the course of 2 days is quite a reasonable plan. So we take that and we start doing some comparisons and building site built systems, no matter what products we're using, what heat pumps we're using, right? It's a custom process in sizing to the building, creating a system design of heat pumps, tanks, and all the other things in a place on a building. They could be open on a rooftop in LA, or they could be housed in wood frame in Seattle, Washington, or some kind of protection in New York City, right? All of those things are going to happen. And this one by one solution requires a large team, a lot of design, and a lot of transfer of information to installing contractors, uh, and then startup, right? Because this is a little bit different. There's a lot of moving components, and and it's a little bit different than working with a boiler, even starting with the sizing, as we'll see. So we can compare and contrast these two plants. So above, that's a plant serving that building, and then our pre-manufactured plant is right below. Those two plants are about the same size, very similar size and storage. The blue plant at the bottom has a little more heating capacity, another 15,000 BTU an hour, something like that. You can see the single point landing, and it's ready to set. That actually went out to a site, and it's working at a site in a building today, and it literally just goes out, screws on the ground, connect the power, connect the water, start it up, and you're done. So while while there's some embedded cost in creating a package system, the value kind of transfers all the way down through it. And this is something that we can do reliably, quickly, and at scale. So again, we kind of stepped back and steered our company in this direction. And we want to be involved in really kind of all the key decision points. So starting with looking at the building, working with sizing, creating the design out of a catalog of products that we've already got engineered. And later in the presentation, we'll see that we have really a lot of solutions that are ready to go. And so we have full factory assembled skids like we're seeing there. We'll see some semi-assembled droplets, which are more friendly to different applications where we don't have a place to put a big skidded system on a housekeeping curb, right? We've got some systems that'll adapt to where the building is, what the design is. And then so we'll be able to present with our distributors full system pricing. The distributors can work locally with engineering as the project is developed, and contractors as the projects move through tender and into installation, as well as startup. We always want to be in hand for full skid startups, and we're always involved in startups. And as we see later in the presentation, we've got a new level of connectivity that we've built into these systems, which allow us to approach startup maybe a little bit differently, or a little more data-driven ability. And then everything we make, we put a factory warranty. So any of the products, any of the contents within the products, swing tank, heat pumps, piping, anything is under our warranty. So it allows the industry to kind of de-risk and step away from kind of that funny finger pointing of there's one component in a system that has 80 different parts, and that one component is nobody's really knows who's in charge, and really what the issue is, because it's a whole system design, and really what to do about it. So our goal is to be that one contact point from beginning to end in long-term operation of the plant, and just bring a lot of value. So we'll start looking at actual applications now, and we'll look at how do we approach a building. So heat pumps are different, and heat pumps really depend on storage, right? So boilers, we look at a building load, we establish load, and then we just bring enough recovery to kind of cover that load. So it's a fairly simple way of looking at it. And heat pumps are not that. Heat pumps always have much slower recovery. And the way we serve a building is we serve it through storage. So once we understand what that load is, and that morning peak in this particular building is actually a collection of buildings in downtown Seattle that we took these numbers and graphs from. Once we understand what that load is, really our next step is to create storage to size to that load. And the heat capacity then is placed to recover that storage in a reasonable amount of time. And reasonable amount of time can vary. There's different goals. Not everyone's going to have the same goal of a super fast recovery. Some are going to be looking at connections to renewable energy and trying to pick up that renewable energy and leverage it as far as possible, which maybe makes you look at recovery a little bit differently. It's just data. We can handle fast recoveries, we can handle slow recoveries. We just really want to start understanding what the load is and then building storage to serve that load. So the way we do that these days, it's different. There's a tool online. It's a free tool. It's paid by public utility money. It's developed by Ecotope in Seattle. And it is a central heat pump water heater sizing tool, and it's really good. And we've used it for a number of years. So one of the slides here will have an address, and we'll be sharing these slides. So you'll have access and be able to find it. It's really easy to Google EcoSizer and it'll pop right up. So in any case, we go to this tool and we start understanding the building. Simple way we can look at it, our team does this literally every day, is we can select, kind of people in apartments and start getting occupancy rates down. So I've just got a sample building here on the left, and I'm just playing around with 50 studios. And the next column over under occupancy rate is a drop down, and I can choose a number of occupancy rates: ASHRAE market rate, ASHRAE low, California low income. There's a number of choices, and that'll give me a fraction, a decimal number to kind of work against. And then next column over is peak gallons per person per day. So that's really how we size and measure domestic hot water, because domestic hot water is used by people in the building rather than the number of one-bedroom units, two-bedroom units, three-bedroom units. So once we actually put a number of people in the building, the next thing is like, how much domestic hot water are they going to use a day? So there's a drop down there too. ASHRAE low, ASHRAE market with low flow fixtures. There's a number of choices. And if that's not enough, if people are good enough and they really understand the nature of their building, because it might be a little bit different, you can grab that blue dot in the center where it says 25, and you can slide it left and right. And you can create your own peak rate, peak gallons per person per day, and really drill in and customize it. From there, we work on the left-hand side, or sorry, the right-hand side. We work with the design cold temperature. It might be 50 up here. It might be 55 in California. And some parts of California, we know it's very seasonal and might drift up to some higher temperatures, but we plug in a design cold number. We select a supply number, 120, 125. That's our mixed value out of the system in hot storage. And for us, hot storage is always 150. So once we get that data in, and then we're choosing a couple of plant types down below. We select the swing tank because that's the basis of our design, and then we're ready to start getting some outputs. And the outputs are essentially taking all those occupancies, gallons per day. There's a couple other questions that you run into, like what the recirc losses are, and you can kind of work with aquastat fractions and storage efficiency, and you can really kind of fine tune things. But at a high level right now, if we go ahead and do that sizing, it's going to come back for maybe this other building on the right where total occupancy of 90. It'll come back with a recommendation of 433 gallons. And this is without any load shift. This is just standard market rate, a market rate system. It'll have a heating capacity of roughly 98 kBTU an hour. We'll actually do a little check because we always want to know what that recovery rate is. So when we size our heat pump equipment and we apply a recovery rate, we do a little bit of math. It's actually, I didn't show a picture of our sizing reports, but we have a sizing report that we can work with, kind of the sales engineers of our distributor partners, and they can come back with a full sizing report that shows a recovery rate. So if we're getting a recovery rate in 4 hours off of primary, that's pretty reliable. At this point, doing this many, many, many years in site-built and full package systems, we really haven't had any undersizings or cold water calls. We've had some interesting buildings where we kind of really thought it was undersized. They got put in, we made allowances to be able to add some heating capacity onto it. And at the end result, what really happened in the couple of buildings that I've seen is there was no cold water call. Once we're fully occupied and everything's running right, what we found was that the undersizing and recovery just made the heat pump run cycle drift past its kind of recommended 16 hours a day duty cycle or 66% duty cycle and run into 18 hours, and maybe we saw a couple of 20 hours. So really undersizing in the heat capacity really just affects recovery time. And recovery time's a decision, right? We can make decisions about this. It doesn't have to be a hard, fast number. But storage is the important one. So all these buildings had enough storage to serve. They had enough recovery plus storage to serve all the loads in the building. So our experience with these eco-sizer um, sizings is they're roomy, they're adequate, and and we're not really overly concerned about looking at that heating capacity and then applying an N plus. We're really about sizing to that heating capacity and sizing to that tank volume because oversizing brings its own problems. And at the end of the presentation, we'll look at a building with data that's just getting occupied, and oversizing and newly occupied buildings kind of show the same attributes. So we'll take a look at that. But that's kind of the outputs, and from the outputs we have a system design. So single pass design's pretty much always the same. It's all about primary storage right there in the center. Size the storage right, and then to the left you build a recovery rate that'll recover the primary storage in the increment that we want, and then we move to the right to the swing tank. And in single pass, especially CO2, the swing tank is really important. Swing tank you don't use in multi-pass. You definitely use it in single pass. And single pass has got a lot of really good attributes once we get that swing tank working. So the swing tank function is on the right-hand side of the screen, we see that blue graphing. Essentially what happens is when everybody goes to sleep, there's no load. And because CO2 really wants to work with these cold standard city water temperatures, 50 degrees, 55, going into the heat pump, they can apply their 100-degree lift very efficiently using the transcritical CO2 and not a whole lot of compressor energy. Um, then they can deliver that high temperature water out of the heat pump plant and pop it into storage, and then just keep moving that cycle until we've charged storage up completely. And everything works really well. If we bought recirculation, if we send it out of the primary across the mixing valve out to the occupant loop and then brought it back through the recirc pump, we store it 150, we mix down to 120, we send it out through the loop, and we've got a recirc return temperature of 110. If we brought that back to primary storage, we'd stir that tank, we'd lose that blue stratification in the tank. And then when that higher temperature water goes out and looks for that 100-degree lift, it's gonna have a harder time because we're working with transcritical CO2. So we just got a whole lot of energy, and we really need to drop that energy. So we want to protect the primary storage tank to keep that stratification in place. And the way we do that is we take the primary storage high temperature water out of the primary storage and put it into the swing tank. And the swing tank is called a swing tank literally because the temperature will swing up and down depending on the time of day. When there's a load, full temperature water travels out of primary into the swing tank, and travels through the swing tank out to the mixing valve and out to the load. It's steady and constant. Swing tank maintains a higher temperature because it's constantly being refreshed by primary with full temperature water. But on the right, when everybody goes to bed, there is no load, and we've got recirculation, and we're going out across the mixing valve, coming back quite a bit cooler. So sooner or later, we'll cool that volume. And so that little red squiggly line up at the top on the right-hand side where it says from EcoSizer output, that's the swing tank volume recommendation volume, as well as swing tank resistance element from that project we just looked at. And so it's basically saying we've established what we think the losses are when there's no load on the distribution loop. And in that cycle, in that overnight cycle, we need to be able to make up those losses. So we'll add enough electric resistance to cover those losses. And when the tank starts dipping, then the electric resistance will see it and it'll come on and bring that temperature back up. In the morning, where we look at that in low overnight hot water use, and we start moving to the right and we see occupancy start take water, then the swing tank's done its job. There's load. We've got more full temperature water coming out of primary, flooding the swing tank, bringing it back up to full temperature by heat pump instead of electric resistance. And then the load continues throughout the day and the system is reset and started. It's the swing tank is just there to maintain the stratified layer, which will then in turn give us these great COPs and this great operation. And 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 it's got a little electric resistance just to cover those overnight lows. It's important the way these things are piped to maintain those relationships. And by our design and factory pre-piping, we're really good at being able to do that, right? Because we're making full systems, not just a heat pump, full domestic hot water system. So we're really actually touching the entire operation of the system all the way through startup and operation. So essentially, what we do is we take that design and we turn it into a product. We've got a whole lot of products, a whole lot of sizes, because everything is pre-engineered. And essentially, it's like flipping through a catalog saying, okay, my building's 90 occupants, and well, it's 90 occupants, and I'm assuming this gallons per day per person, and other attributes, and I'm looking at that output and saying, okay, I need a heating capacity of 97 kBTU and 500 gallons of storage. I can flip to the WaterDrop catalog and find something that's like 96 kBTU and 500 gallon storage, all prepackaged in a single skid, and any number of solutions. So that's really what we do as a central, a fully packaged central heat pump manufacturer. And now we're going to start taking a look at how we deliver. Is it all skids, or do we have the ability to adapt and put tanks into tank rooms? And yeah, we can do all of that. So the basic product mix starts with the skids. This is really what a skid looks like, just kind of blown up and taken apart. Um, Primary storage tanks, swing tanks. Swing tanks are actually getting smaller. More research around swing tanks means we can kind of cut volume down, um, and operate them a little differently. It's always a little bit of new research going on. Expansion tanks, lots of piping, mixing valves, research pumps. So that would be a single plant ready to serve a building. And if we have a bigger building, then we just start adding a secondary skid. And a secondary skid in this case is more storage and more heating capacity. Because the primary skid has already got the recirc, the mixing valve, the controls. It's got a power landing for itself. It's got enough expansion to cover itself. So as we grow, as we grow the plant size to serve larger loads, then we can start adding secondary skids. And we've got a range of sizes to work with. That's what it actually looks like being manufactured in the shop. Today, that single plant is up on a building in Northern California making domestic hot water for a whole number of apartments. And I think that one's roughly 800 gallons and a heating capacity of 140, 100, yeah, 120 to 140 kBTU. I can't remember off the top of my head, but that's it. And you can see right in between those two are jump pipes. So up at the top, in between the two skids, are some 2-inch and 1-inch pipes sticking out. And essentially, you set those two skids together and connect those pipes. And on the right-hand side, below that recirc pump, are the building connections, kind of next to the red expansion tank. So we do the building connections on the right-hand side, set up the jump pipes. There's a low voltage jump pipe also. Each skid has its own power landing, and you can literally set them in a day or two and add that piping, and then spend a half a day to a day in startup, and the plant's up there and fully operational. So we also have the ability to work with existing buildings and new construction buildings that really are better off with a tank room design, right? Architectural's already done its thing. They're used to tank rooms, and for one reason or another, you want to put anything on a roof. This is a building with a tank room. It's up and running, still gaining occupancy right now, so it's a fairly recent building. And in this building, the design wanted to have more electric resistance backup. Doesn't need to be. We're really comfortable about not having extra backup resistance, but those two Bach water heaters are probably picking up a little redundancy that will hopefully never be used. Because that's a lot of swing tank. And on the upper left, you can see our folks are standing in front of what we call a droplet 12, and it's roughly about 186,000 kBTU. And those are two 500-gallon storage tanks, the spray foam tanks in the back. And that's a pretty good match. And then one more swing tank would meet it. However, it doesn't matter. This is the world of water heating. Everyone has different reasons and different design goals, and we're here to help everyone kind of meet those goals. So we can have heat pumps outside on a pad, full control box. You can see a control box with kind of a little blue writing on the left-hand side of where the guys are standing. And that's got the power landing. It's got all the controls. It'll reach in, understand the tank temperatures, operate the entire system from that box outside. And it'll do it in cold ambient, rain, snow, cold weather, sub-freezing, doesn't really matter. CO2 is really, really, really pretty amazing. So we've got a lot of adaptation, and along with full skids, then we've got these racked heat pumps that we call a droplet. So we're back looking at a droplet 12. It's sitting on a yellow transport pallet just so that someone can pick it up with a forklift and wheel it around and move it. It's a tall, skinny application. On the right-hand side, you can kind of see there's two water pipes, cold water at the bottom and hot water out at the top. Comes fully wired, fully insulated. It's got controls, and it's ready to mate with tanks. And because as we get into the system design, where the industry is going, and the fact that electricity costs money, then we developed a new series of tanks that are a companion to the skids as well as the droplets. And you'll see that they have four thermistors. Those are what those holes are. So we can use single tanks, multiple tanks. We'll get into more multi-temp and why and what we're going to do with that. But we've also built in on the right-hand side, you can kind of see, this is a front and back. See if yeah, there we go. That works. Okay, so I've got a couple of Ethernet ports, right, in the side of the panel. And essentially what I'm going to do is we'll set that, we'll attach it, we'll get it plumbed. And if we want more capacity, then really all we need to do is sorry. Yeah, jumped ahead a couple is add more capacity. So these droplets come in many sizes, and at the end you'll see we've got a whole product range and so forth. But we can gang these droplets together, so we can put one droplet 12 with another droplet 12. We can add a third droplet 12, so we can push that all the way out to 554 MBH total heating capacity, and then pair that with a number of tanks, and we've got some real good capacity there. Hopefully I can get rid of that annotation. Well, maybe. There we go. Thanks there. No, as quick as I like to be on that. Okay, so now we can gang them together and we can pair them with a new series of tanks. As of today, we actually have two more tanks. I think we have a 580-gallon tank, or maybe three more tanks, 700-gallon tank, and roughly an 800-gallon tank. All designed around how our systems work with multiple thermistors, and there's a multiple thermistors allow us to do some really cool things that we'll see later on. So we've got kind of the heating capacity in the droplet racks and then a tank family. And so we can really pull together some basic designs and supply tanks into a tank room. We can work with other tanks. We don't really have a lot of restrictions around that. And so, really, when we step back and look at it, we've just got a lot of different products to cover multiple applications from very, very small buildings all the way to some pretty good sized buildings. And we've got a team that's ready to just take in the information of the building, work on the sizing with anybody, help develop the project with our distributors who are really good, high skilled sales engineers in the market. The world of water heating is really very new, so we're all doing a lot of learning, but we've done this a while and it's working really pretty well. So as we continue to build, we've got a lot of choices for racks and tanks and droplets and things. So we'll take a quick look at manufacturing. We manufacture here in Tumwater, Washington. We set a brand new plant. That guy on the picture of the window is the researcher who we got to work with a number of years ago and has since passed. And he's been a good friend in the industry, so we like to wave at him on the way into the building. And as we go in and we look at some of the assembly stages, we just set up a factory to make heat pump water heaters in full skidded fashion, create designs that have 100% backup, right? Because we're using multiple individual heat pumps, each with its own compressor, each with its own water pump. They're all manifolded together. So even if one goes down, we've got a number of heat pumps that can continue to operate in this potable configuration. And as we understand, really, if one goes down and we've got 12 or 6 or whatever the number is, all that effect is it just slows down recovery of primary storage. Doesn't really affect serving the load, which is why we really like this system in CO2 so much, because we're serving the load with stored energy in the storage tanks and then just recovering that energy with the heat pumps. We add some three-way valves so they're easy to inspect, repair, valve off one heat pump and do a back flush. These things, need to be maintained, so they're built to be maintained. Everything we do in all our manufacturing steps start with building all systems in SolidWorks. So it's a predefined, all those individual piping components are individual part numbers in our bill of materials within our ERP. So we've got a constant flow of orders. The orders demand that our purchasing department purchases products and that fabrication gets a list of materials to cut for the next steps of production, and away they go. So it's very much a process-oriented production facility. And we build our own and work with an outside partner on UL 508 panels. We embed our own controls into it, and we have a number of solutions for connecting primary and secondary water heaters, piping them together. And then as we go through production, final stages are inspection. We've got a test bed where we can actually plug in wet systems and do a full functional test. And actually, these days now, we do a cloud connection so we can actually see the system. We'll look at that here in a little bit. And then skids or droplets are ready to go out, get loaded on a truck, and set out for delivery. So we'll take a step back and we'll talk about controls and management now. Things have come a long way, and we have spent years developing our controls. And the controls are really very good. And so they've elevated to the point where we call it the domestic hot water manager. And the domestic hot water manager is a controls and connectivity um, system that's embedded in every plant, every product that we ship. Every product that we ship comes with an LTE SIM card so that we can actually see it as the system gets powered up, and our engineers can watch the system and help startup. Everything comes with 4 temperature probes for our WaterDrop high resolution series tanks. It comes with a CTA 2045 skybox so we can run grid flexibility. We're adding more metering right now. We've got ambient air temperature, incoming water temperature. We're just shipping, I think today or tomorrow, the first systems that actually have built-in BTU meters so we can calculate system COPs at site in full operation every day, not a full add-on M&V system. This is just embedded in the plant and water pressure. There's a few more meters or data points that are in systems right now. And I would think by the end of next week, those 2 square boxes turn into check boxes. So this is what a panel looks like. This is kind of a version of the DHW manager. It really does quite a lot. But everything's got an LTE network router with a SIM card. So we can see it no matter where it goes. First thing we want to do is get the cloud connection established so our engineers can see in the system as it starts up. You would be amazed at what you can learn when you watch a system start up. You can see all the different heat pump operations, entering temperatures, leaving temperatures, how the tanks are charging. You can see a lot. Everything has a PLC that we can communicate with now by the cloud connection, and we have a skybox so we can run utility demand response and other demand response, our own demand response, and price optimization programs, which we'll look at in a bit. We've got parent-child connections, individual breakers, heat trace breakers for systems in colder climates that require heat trace, and exterior screens. All of this is starting to build out to be able to operate these systems in a very smart and efficient way. So when we pair that ability of control with a tank series that has multiple temperature probes, we start looking at those tanks like they're a battery. And we've got a manager that can look at it like a battery so we can understand its state of charge. And because we're servicing off of storage, state of charge becomes really, really important. Like when you're in San Diego and the peak rate, peak electrical rate or electricity rate is 80 cents a kilowatt hour, and you want to avoid buying that 80-cent kilowatt hour. You're working with storage, you understand your load. There are ways that we can manage how these buys and make the system operate a little more effectively. So because droplets and tanks always change and buildings are always different, we designed this tank series so that the thermistor probes can just be plugged. They come right out of that control panel. They can travel a distance, and we can go quite some long distances, but they'll map to various tank locations across our series of tanks. So the top line is, tank thermistor 1 through 4 vertically, but as you start adding more tanks, those positions shift. The the thermistor 1, 2, 3, and 4 at the top represents 20% aquastat fraction, 40% aquastat fraction, 60 and 80. And really all we're doing is stretching those same relationships across multiple tanks. And to our controller, it just understands whether it's 300 gallons of storage or 1,500 gallons of storage. The relationship in the aquastat fraction is really the same. We developed solutions to be able to place heat pumps and storage quite a long distance away, manage it by a number of operations. We've developed a child mech room controller where we can bring just a single Cat 5 down from the droplet, maybe on the roof, and there's a tank room at grade. So Cat 5, bring it down. The mech room controller's got another PLC. It can run pumps. It pulls all the tank temperatures out of the tanks, and then we can task it with doing some additional things. So extension kits are really kind of two ways. It's a pump option, which we're just beginning to deploy now, or it's also a braze plate heat exchanger. The braze plate heat exchanger kind of accomplishes some tasks in maybe areas where the water quality is a little bit questionable. Maybe it's a little hard, and a braze plate heat exchanger, while we do get some temperature loss, and we got to really be mindful of that, we've got something that's a single service point instead of multiple service points across each of the gas coolers of the heat pump. So it's something that we offer and we work with. And also, if we're in an area that's got extremely high water pressure, it's a way that we can manage these water pressures and differences or distances, sorry. But either way, we've got options where we can work with large separations across uh, multiple um, multiple applications. So quickly, kind of moving here, um, as we move into the energy management side of things, this is where it's really interesting, bit exciting for me as a part of the industry is that all these buildings use energy and the owners need to buy energy. The industry is heading towards central plants having these CTA 2045 connections so that the utilities can operate load up programs, normal operation programs, shed operations. These are all signals that the utilities will begin broadcasting, and our equipment today is able to receive those signals and operate on those parameters that the utility is broadcasting. And essentially, the goal of the parameters is to just just time maybe when the energy is purchased to build up storage and operate some grid flexibility. We've got our own ways of doing that, but our goal is if a normal central heat pump water heater plant is here in the red and the gray area is our peak rate where electricity is the most expensive, then we really don't want to run heat pumps there. We'd rather be like the blue. And in order to make that blue where we don't buy any energy, the way we operate that is we look at storage, we understand it, and we run a load up configuration. So before we get to that gray peak energy zone, we run some signal encoding to turn the heat pumps on the appropriate numbers so that we arrive at that period with full storage. When we're in the full storage, depending on how we size storage, and there's many systems that oversize storage to accomplish this load flexibility, we essentially can just ride through the entire period of storage. So we can do that because we're connected, we're cloud connected, and it really gives us a lot of options. And maybe the one of the last things I'll be able to share today is that we are developing one more feature that kind of brings all these pieces together. And this is a client-facing piece of information. This is a particular building right now, and it's got some interesting aspects, I think, for me. But this is just kind of like a little draft beginning point of what a client-facing dashboard would look like. And you've got tank condition at the top, you've got tank temperatures, and the green squiggly line is incoming water temperature. And those behaviors of that green squiggly line make a lot of sense to me. The tanks, there's not a lot of activity with the tanks. And then we go down at the bottom, and those are heat pump runs. So we can see moving from left to right. I don't really kind of look at where that period was. Looks like it's early January. And we can see there's a solid red line. So stage one has been operating for a long time. And these other stages kind of come on and off really fast. And this is indicative, and the tank temperatures kind of slowly coasting down of what a new plant looks like before the building gets operated. We're probably going to run out of time to kind of talk about this, but there's a whole characterization of central heat pump water heaters as they get installed, and they might have to wait a few weeks for occupancy. And so it's interesting. We have conversations with the teams and the contractors as they're going in and getting, sampling domestic hot water out of the plants when the building's been sitting for a long time. But there's data now that we can see through the cloud and dashboards that we can understand that. So, in kind of closing, we've got a number of projects out, and here's one in Northern California. I think this is the one that we saw in the shop, and multiple heat pumps serving a very, very large building, a few different zones, and they start up, they function well. Retrofit buildings, we can sit on a pad on the outside, pipe through the ground into an existing loop. And then we, get to our website, which is a great way to reach out to us. We've got a lot of contact information and a lot of info and a lot of information available on submittals and design and so forth. And with that, I made it through that presentation. Thank you very much for your patience and interest, and hopefully, it was worth your time.
Great. Thank you, Albert. Because we are at the 1 o'clock hour, just one quick reminder that this presentation was being recorded and you will all receive a copy to your email address in about a week. We do have two open questions that I'd like to lob your way, Albert, for some discussion for those of us that can hang around for a little bit longer and keep talking about water drop. All right, so please talk a little bit more about not needing a defroster. To pull heat from outside, the coils need to be colder than outside air. That leads to frost on the coils.
Yeah, okay. So that is correct. So the cool thing about CO2 is that right when we put it under pressure and it's high temperature vapor and so forth, we run it through the gas cooler and then send it down to expand and head out to the evaporator. You can make the refrigerant really cold, colder than normal. So you can get some really cold fin temperatures. And yes, you'll get some really cold fin temperatures. Um, so when we get into a defrost mode, rather than a reversing or something like that, essentially the way these CO2 systems work is it's a hot gas bypass. So we've built up some high temperature, high pressure vapor, and really all we're going to do is we're going to take some of that high temperature, high pressure vapor and run it across the evaporator coil and burn off the frost. Doesn't take a lot. Meanwhile, the rest of that refrigerant is still going across the gas cooler with an operating water pump. So we're still able to increase the water pump speed, sorry, to maintain that 150-degree leaving water temperature based on the refrigerant that we have running through the gas cooler, while at the same time burning off frost on the evaporator coil on the outside. It happens, obviously very frequently, depending on outside temperatures and humidity and so forth. It's great. We've got systems independently monitored for years. And there is a D rate that one should apply because we are, sending a little bit of that refrigerant out and there's a little bit of expense. It is like nobody, including independent researchers, have come up with a meaningful D rate. It's just like a non-factor. So hopefully that helps. And if we want more follow-up, I can do my best, but I can't say that I'm the smartest person ever on this subject.
We'll call that case closed for now. All right. Hello, Great Looking Systems. Do they have OSHPD/seismic certifications, or is it case by case?
We built all of our frames with seismic value, and our submittals specify fasteners, and we have full seismic reports. We have had we've had really zero issues meeting seismic requirements, and every once in a while in our droplets, somewhere they might have a different wind load value, which means somebody's got to look at the anchors.
All right. And then I can't tell if this was pushed too early, but someone just says, hi, Albert.
I bet.
Okay, here we go. Oh, the OSHPD relates to to shaking the panel.
I might need a side conversation on that.
All right.
I might not be able to answer that right now. Okay, yeah.
Yeah, to further converse about that, info at waterdropsystems.com, and the team can fully dive into that topic.
Hmm.
Okay, looks like no more open questions as of right now. So I think this is a good time to wrap it up. So Albert, thank you so much for a great presentation today. Thank you, Ben, for your wonderful and informative behind the scenes work on the Q&A section. Lots of good stuff answered. And then thank you everyone for logging on and being a wonderful audience. You are why we are here. And then another reminder, never hurts to remind, you will all receive a copy of this presentation to your email in about a week. And then if you'd like to learn more about WaterDrop Systems, please get in contact with the WaterDrop Systems through the website or through your local distributor, which Albert had on the slide right there. So thank you, everyone, and have a great day.
Great. Thank you.